Alright, this is 7-5, applications of triangles. So we're first going to talk about these two specific angles. One is called the angle of depression and the other is called the angle of elevation. These two angles are called what they are because of their relationship with a horizontal line. So an angle of depression is found below a horizontal line, so it's angling down from a horizontal line. And the angle of elevation is found above a horizontal line, angling up. So we're going to talk about sort of how we can use the information that we've already talked about to solve real-world situations. Some of them are a little bit less than real world, and you can laugh at those with me later. But these actually do have applications in real life, and we'll talk about some of those applications. The first section here is about similar triangles, and we're just going to use similar triangles, the information that we have from prior lessons about similar triangles, to answer these questions. So the first one is about Sharon, and she's trying to figure out how tall a tree is. At a certain time of day, she measures its shadow to be 14 feet long. She then realizes she can cut out a triangle with paper that matches the length of the shadow and the height of the tree if she holds it up in front of her. Use the similarity of these two triangles to decide how tall the tree is. So really this is a similar triangle problem. We have her small triangle that she's cut out in front there with 5 inches and 7 inches. And then we have 14 feet measured as the shadow. So the way that we solve similar triangles is we try to decide what the growth factor is between these two numbers. And what I want you to do is kind of ignore the inches and the feet. The tree is definitely going to be measured in feet because its shadow is measured in feet. But because different measurements convert proportionally, we don't actually have to convert anything here to make this work. So from 7 to 14, we multiply by 2. Hopefully you've seen that by now. Finding the growth factor would be like dividing 14 by 7, and you would get 2. And so we do the same thing with the 5 inches here. We multiply 2 by 2, and then just measure in feet. So the tree should be 10 feet tall if we use that growth factor. A second question here, if the angle of elevation from the ground to the top of the tree, so we are talking about this angle, that's elevation, is 48 degrees. What is the angle between the tree and the imaginary line connecting to the tip of its shadow? So this is this angle here that we're talking about. So we're assuming the tree is growing at a 90-degree angle from the ground, and using that information we can subtract 48 and 90, sorry, I'm writing this incorrectly. 180 minus 90 minus 48 equals 42 degrees. So this is a 42-degree angle there. Great. So another similar triangle thing that happens in real life is with mirrors, and this is kind of interesting to me. The description up here says reflections in mirrors also create similar triangles. When looking into a mirror placed on the ground at the top of the object, the angles created by your line of vision and the ground are the same. The angles at the base are 90, and therefore the third angle in the two triangles will also be the same. So that description is just telling us that we have 90-degree angles here. These two angles are the same, and then so are these two angles. So we have a pair of similar triangles created by your line of sight and the thing that you're looking at through the mirror, which is kind of weird. I don't know if anybody has tried this before. I don't think that I have. The first question says, Jake places a mirror on the ground 150 feet from a telephone pole and finds he can see the top of it in the mirror if he stands 7 feet from it. Use Jake's height to find the height of the telephone pole. So again, we have a similar triangle situation. The two corresponding sides here are 7 feet and 150 feet. So if we were to find the growth factor between those two numbers, we would have to divide 150 by 7 to figure out what the growth factor was. I believe that gives you sorry, I need to grab a calculator. 150 divided by 7 is 21.443-ish. And then we use that growth factor to do the same thing with 5.5 feet to see what that telephone pole is. So we do 5.5 times 21.43, and we get, I believe, 117.86. A really tall telephone pole. This is one of those where it's like, oh, is that realistic? I'm not sure, but we could certainly find a realistic situation to use this in. I think maybe the numbers are just need to be adjusted so that that's more realistic. Anyhow, fantastic. So we have that similar triangles. We also have a bridge here. The bridge was built using similar triangles. Use the smaller triangle to find the length of the side of the larger triangle. So we have two triangles here. I don't know if you can tell. Let's highlight. We have a pink triangle, and here's our yellow triangle. The growth factor, or I guess the corresponding sides here, would be 6 feet and 9 feet. So if we do 9 divided by 6, 9 divided by 6, that gives you 1.5. And you can do the same thing for the 4-foot side of the triangle to see what x is. So x equals 4 times 1.5, which is 6, I believe. 4 times 1.5, there we go, yep. So x is equal to 6. So that's our similar triangles. There's also some other kinds of applications here. The first being special right triangles, like we learned about last time. So this is, of course, a very silly problem, but it's using the idea of special right triangles and similar triangles, because special right triangles kind of come from the idea of similar triangles. So Steve, our guy, is running from a T-Rex and happens to notice that he can see the top of the dinosaur's head in a piece of broken glass on the ground. He knows his height and the dinosaur's head, and the approximate height of the monster, and he also knows that the angle between his line of vision and the ground is 30 degrees. So we're talking about this angle, and we know that that makes a similar triangle over here because of the reflection. Use the information to find how far away the dinosaur is from Steve. So we're wondering how far away. So we have one triangle there and another triangle here, so we're going to have to add those two triangles together. What we have here is 30, 60, 90 triangles, a pair of 30, 60, 90 triangles. And we have the short sides of both. So we know that if we're trying to look for the other leg in a 30, 60, 90, so I'll draw really quick the triangle over here, 30, 60, 90. If we have this angle, then this side length, sorry, and this one is going to be x root 3, and this one's going to be 2 times x. So we're going to follow that pattern, but with x being 10 and with x being 6. And we don't care about these sides. That doesn't matter to us. We just care about how far away the dinosaur is from Steve. So we have 10 times root 3 for that one, because 10 is x in that triangle, and 6 is x over here, so we have 6 root 3 for that one. And we're going to let's just add those two things together in a calculator, and it will automatically give us a decimal value for both of those. And I think that gives us calculating again. 6 times the square root of 3 is 10.39, I believe, and then 10 times the square root of 3 is 17.32. If we add those two up, we're approximating here because it's decimals, gives you 27.71 feet away. Silly question, but the math is sound. Last we have one where we're using the Pythagorean theorem. So I know we've mentioned this a couple of times this unit, but we haven't really talked about, we didn't learn it because we should have learned it before, but I'll put it here. Pythagorean theorem only applies to right triangles. So you can't use it with any kind of triangle doesn't have a right angle in it. But if you do have a right angle, you have sides A, B, and C like that, and you can find missing side lengths just by plugging the side lengths in that you have, and then solving for the rest. So in this particular triangle, it's a suspension bridge. A company needs to decide how long one cable from the tower to the bolt on the bridge should be. The top of the tower stands 100 feet above the bridge, and the first bolt will be placed 175 feet from the base of the tower. How long should the cable be? So we're wondering about this cable here. And we're going to call it C just because that's convenient. Not that convenient starts with a C, but that's the hypotenuse, which we always call C in the Pythagorean theorem. And then we're going to just plug in what we know. So we have 100 for A, and then 175 for B, and then not sure what for C yet. 100 squared is 10,000. I have 4 zeros on there. 175, and I'm not sure what this one is. 175 times itself is 30,625. And if we add those together, oops, that should be C squared. If we add those two together, we get 40,625. And the last step here is that we square root both sides so that we can figure out what just C is instead of C squared. So we're going to square root, making sure I'm hitting the right button. That gives us C is equal to 201.56, particularly feet. So I'll write that up here, 201.56 feet. Pythagorean theorem is truly useful a lot of the time, so it's a good thing to remember and keep in your brain about this. A squared plus B squared equals C squared. I'll just highlight it just for fun. A and B. You know what? I take that back. I'm going to highlight C pink because I drew it pink on the bridge. There we go. Good. Okay, so that's all the problems I have for you on this applications lesson. Let me know if you have any questions.